Question 2 focuses on LTL versus CTL. So CTL and LTL are both subsets of CTL star, which can express all properties available through LTL and CTL. However, efficient model checking algorithms have been developed for both LTL and CTL. So basically the model checkers have been created for LTL and CTL. So you can see here a diagram. CTL star composes everything of LTL and CTL. You also note that LTL and CTL, there is an intersection, slight intersection between them. So you can express some properties in each other. However, you also see that there are some parts of CTL cannot be expressed in LTL and vice versa. As we can see from the diagram above, there are some formula that intersect between LTL and CTL, as we just said, but there are also formula that cannot be satisfied by the other. Not all properties satisfiable through LTL can be achieved by CTL and vice versa. An example of this is below. So we have our model T, which starts in state 0, where the atomic proposition P is true, and it can loop infinitely in state 0, or it transitions to state 1, where not of P is satisfied, and then it transitions immediately out to state 2, which again loops infinitely in state 2 where P is true. So always, eventually always P. So this is LTL formula. Can we express this with CTL? So this crypto structure satisfies always, eventually always P, an LTL formula. So let us look at possible executions. See if I can bring, yes. Let us, okay. So one possible execution is that it stays an S of 0. So S0, 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 S0. And we're focusing on the LTL formula. So our formula is eventually always P. Another execution, it can go state 0, then go to state 1, and then it immediately goes to state 2, and then it goes in state 2 infinitely. And you can also do state 0, you can loop infinitely, then go state 1, but once you go to state 1 you always go to state 2. So what are the outputs of this? So we have P, 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 and so forth all the way on, always P. This is P, not P, 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 and this has P, P, again, not P, but then P. And once you're in state 2, it's always going to be infinitely P. So eventually always P is our LTL formula. So that's saying we eventually end up in a state where it's always P. And you can see that this is true for all LTL traces. If you start in state 0 and you keep infinitely looping in state 0, you always end up with P, P, P. P is always true. Eventually always P, so it's always going to be P. In the second execution, it starts off as P, then it's not P, but we're not saying always P, we're saying eventually always P. So if you're in state 1, you can't loop infinitely in state 1, you have to go to state 2. And in state 2, it's always going to be P, so it's always P. So eventually, you're going to end up in a state where it's always going to be P. So again, this is true. And again, the third execution, P, P, you go to state 1, not P, and then you go to state 2, and it's always going to be P from here on. So eventually, we always end up in a state where it's always going to be P. So you can either stay in state 0, or go to state 1, which always goes to state 2, where it's always going to be P. So this can be expressed in LTL. As you can see here, it's in green, it satisfies F, G of P. Now, let's try the same in CTL. Now, for here, our formula is A, F, A, G, P. Now remember, as we said, with LTL, you can assume that there is an A in front of here. So for all paths, eventually always P. So you can assume that there is an A. And you can see for all paths, eventually always P holds. However, in CTL, we cannot do always eventually G. So A, F of G, P is not allowed. You're not allowed to do that. We put a line through that. Because every temporal operator, or every quantifier, must have a temporal operator. You only have one temporal operator per quantifier. So the closest we can get is for all paths, eventually, for all paths, always P. And we can see immediately that this is not the same. So let's just do some executions like we did in the previous. So we start in state 0. This can go to state 0 and go to state 0, etc., all the way on. Or you can go to state 1, which goes to state 2. And once you go to state 2, it's always going to stay in state 2. And again, here this can go to S1. Let me just draw. State 0. This goes to state 2. And this stays in state 2. So again, let's do our outputs. We have P from here. We have S1, which is not P. We have P. We have P. And this goes on forever. So again, P, P, P. Not P, and P. So, when we're dealing with the CTL formula, we have to start with the inside. So we start with always, for all paths, always P. Now, we can see, so this is saying for every path, for all paths, always P. Now we can see P, P, P holds here, but P, P, not P. So we have an error here, X. Let me use black. Does not hold here. It also does not hold here. So this does not hold. So if this does not hold, this does not hold it. So this is not true. And as we can see here, cryptic structure T does not satisfy for all paths eventually, for all paths always P. So you can see that these are not the same. So FGP, which is LTL formula, is not the same as for all paths, eventually for all paths always P. That just shows you that certain things in LTL cannot be expressed in CTL, and it also goes vice versa, as we see in the next question. So this just explains the same thing again. Here we can see the crypto tree satisfies the LTL formula, meaning there's a path where eventually P is always true. Example path executions on P are, so these are the same as what we've done on the whiteboard, and there's no CTL formula that can replicate this. The closest we can get to is this. So again, this is just the same thing. Enclose the CTL formula in parentheses, so AF, AG, enclose the innermost, run the innermost formula, AG of P as we did earlier, and you'll see the only path that satisfies it is if S2. However, S2 is not the start node, you start in S0, so you have to go through these, and you can see it's not satisfied in S0 or S1. If you were to start in S2 and you looped infinitely, then it would pass. But we start in S0, and in S0 you can go to S1, therefore on all paths it's not always P. And then again, when you run the outermost, you can see that it doesn't hold in S0, because in S0 you can go to S1. Yeah, so you can see that we have a statement path that does not satisfy this formula. So that is question 2, which is just LTL versus CTL.